Today I just want to share a little bit about the future of dark matter from my perspective as a Black feminist theorist and a theoretical physicist who works on the dark matter question. I only have a little bit of time with folks today, so I'm just going to point out that I actually have a book out right now, The Disordered Cosmos, A Journey into Dark Matter, Space-Time and Dreams Deferred. I'm sorry, can I ask people who are in the background for me to stop talking? Thank you. So I'm mostly a dark matter theorist. I'm also a bit of a neutron star observer, as was introduced, and I'm a Black feminist theorist. And one of the reasons that I'm making a point of sharing these facts about myself again is because it's important for me to contextualize what I'm going to say, that I became the latter so that I could stick with being the former. So part of the premise that I want, if you remember nothing else from this talk, I want people to remember is that we all have a right to know and love the night sky. This is one of the key points in the book, which again contains much more than I'm going to be able to say to you all today. And the journey that I want to take people on is to give people kind of a compelling reason to think about why we do physics and astronomy, and to think about the importance of the social aspect of why we do physics and astronomy as people. So Naga mentioned that I do theoretical cosmology, so I want to give people a sense of what actually cosmology is as a discipline. So my job is basically to fill in the cosmological timeline. So what you're looking at here is a totally not at all to scale timeline of the universe from what we call, I will say in air quotes, the Big Bang, because we don't really entirely know what happened, if exactly there was a beginning, what came before the beginning, all the way through to about 14 billion years, which is about how old we think the universe is, although our estimates there are always changing. Up to about the 400,000 year mark, the universe was basically kind of a cosmic plasma goo that was so dense and so energetic that photons could actually travel freely. At about the 400,000 mark, things cooled down enough that there is enough space for photons to start traveling freely through space-time. And we can actually see these photons. And so if you've heard of the cosmic microwave background radiation, that's what those photons are. Because space-time is expanding, the light waves have been getting stretched out. And so today we see them as microwaves because they have been getting stretched out for about 14 billion years. We can also see in the infrared using the Spitzer Space Telescope, images from first light, so first stars. And if you haven't looked at the Hubble Deep Field or the Hubble Ultra Deep Field, this is from the Hubble Space Telescope. I encourage people when this keynote is done or you're done with this event today to look it up. Some of the most spectacular things that you will ever see in your lifetime, I think, are these images that we have seen from the Hubble Space Telescope. And so what you're looking at here in the visible spectrum is tens of galaxies, and there's a whole lot. When you look it up, you will be able to zoom in and see that there is so much detail happening in these images. So in a lot of ways, looking at an image like this, you start to think, oh, okay, so we kind of know about cosmology. What's your job? We have a lot of information about these different moments in the universe, but it is still the case that we still have not been able to fill in the mathematical narrative, how we get from the cosmic microwave background radiation. So these microwaves, these photons from the early universe that are everywhere. So they're surrounding you right now. And they're not harming you, right? We evolved with these in the picture. So you'll see that in this particular figure with the microwave background that there are some different colors. So those colors represent small variations in the temperature associated with the photons, tiny variations, 1 part in 10 to the 5. And those variations are reflections of the quantum fluctuations that will eventually go on to aggregate gravitationally and collect enough stuff that structure starts to form. So in a lot of ways, what I do as a theoretical cosmologist is try and figure out how we get from this COBE satellite data to the Hubble Ultra Deep Field. How do we write down a mathematical picture of this? And clearly, this involves a lot of data. And increasingly, as our capacity to collect data, to build better instruments, and to work with it computationally increases, there's even more data. Our data needs are becoming more important. The other piece of this is that space-time is expanding, and how that expansion happens is dependent on the stuff that's inside the universe. And so that's another reason that we need to understand what this evolution of structure formation actually looks like. So another way of thinking about what we do in cosmology is that we try and answer the question of what is the universe made of? So as a PhD student, I came of age with the cosmic acceleration problem. So we know that the universe is not only expanding, but that actually that expansion is accelerating. So if you think about if you're driving and you're getting on the highway and you want to pick up speed, so you hit the gas a little bit, you're accelerating, the speed is increasing. So space-time is doing the same thing. And we think that that is caused by something called the dark energy, or the cosmological constant. And so I came of age with this problem. It was understood to be a problem my senior year of high school, and I thought about it all the way through my PhD. As a postdoctoral researcher, one of the things that you're expected to do as a postdoc is actually move into thinking about problems that are independent of your PhD advisor. And where I found myself actually was thinking about dark matter. So part of what I want people to take away from looking at this slide is that maybe you came into this talk thinking, especially even after just the last slide I showed you, that most of what the universe contains is what we can see, right? I was just encouraging you to look at the Hubble Deep Field and the Hubble Ultra Deep Field because you can see this like incredible luminous matter in it. But actually luminous matter, what we might call normal matter, the folks that you see on the street, the folks that unfortunately are sometimes mistreated on the street. You're looking here at, for example, Breonna Taylor. We are normal matter. The trees outside my window are normal matter. The chair that you're sitting in, the floor you're sitting on, wherever you are, we are what we think is normal matter, baryonic matter, but we are actually a very small fraction of the universe. The stars are what we would consider to be normal matter, but again, a very small fraction of the universe. So part of what you're looking at here is that most of the universe is made of two things that we don't really understand, and so they've been called dark energy and dark matter. Most of the content of the universe is stuff that we can't see and that we still don't understand. And so one of the reasons that we're doing all of this data collection is because we want to better understand the majority of the matter energy content in the universe. So even though I worked on dark energy for a long time, I don't have a whole hour to kind of give you all an overview. So I'm going to focus on talking about dark matter because that's what I work on now, and I'm very passionate about it. So I want to give you the case for dark matter. So you're looking here at a slide that has a figure on it. And for people who are not used to looking at plots, I don't want you to panic. What you're looking at is a plot of a star's rotation curve around a galaxy. So if you think about a star in a galaxy, it's orbiting the galactic center. On the horizontal axis, you have the distance from the center of the galaxy. And on the vertical axis, we have how fast the star is moving in its orbit. So if a galaxy is only comprised of the luminous, visible, quote, normal matter, even though actually we are the cosmic weirdos, right? We think we're normal, but stuff you can see is weird in the universe. If we think that the galaxy is only made of the luminous, visible matter, then the line that we should see is this orange line. But when Vera, Rubin, and Kent Ford in the late 1960s and early 70s actually went out and measured the speeds that stars were orbiting their galactic centers, what they actually saw was this green line. So you can see close to the galactic center, the lines line up, but then there's a huge divergence. The stars were moving faster than expected. So what this suggests is that we need more mass than we can see, right? There are two options here. We either need more mass than we can see, like there's a bunch of mass in the galaxy that's not radiating, that's not luminous, or the theory of gravity that we are using to interpret this data is incorrect. So I should say that actually modified gravity continues to be an active field of research. It's far less compelling in the context of data analysis, and I'm happy to answer questions about that during the Q&A. So what do we know about dark matter roughly? So primarily what we know about dark matter is that it doesn't produce light, or at least it doesn't produce enough light for us to be able to see it. So sometimes you'll hear about dark matter and people will tell you it doesn't interact with any other force except for gravity. I'm going to soften that a little bit by saying its only significant interaction is with gravity. And importantly, calling it dark matter is a bit of a misnomer because light goes right through it. So it should really be called transparent matter or invisible matter. This is one of my big missions, and I talk about this a lot in the Disordered Cosmos, because it's such a big misunderstanding that people have. Like, my hair is dark, but dark matter is not really dark. In fact, I could have a clump of dark matter in my hands right now, and what you would see is exactly what you're seeing right now. I would feel the weight of it because it would have mass. And so I would feel the Earth's gravitational pull on it, but you would not be able to see it. The light that is coming through my windows would reflect right off my hand and into the camera. So that's our case for dark matter. Galaxies seem to primarily be filled with a bunch of mass that we can't see. And so galaxies are more massive than we would think they are, just based on looking at the luminous matter, the stars in it. And so it's worth saying that more recently, P.J. Peebles, who won the Nobel Prize recently for his contributions to cosmology, in his recent book, he calls it subluminal matter. So it's not that it doesn't radiate light at all. It might actually radiate some light. So a problem that I think about a lot, and certainly the source of a lot of simulated data production and then also observational data production, is trying to think through what we call in the astrophysics community the galaxy halo connection. So I've now just told you the story that we think that the luminous part of a galaxy is actually just a somewhat tiny fraction of what's actually in a galaxy. So about 20% of the galaxy is this luminous part in the middle, like the beautiful spiral that you see from astronomical images. And then 80% or more is in this, what we call the dark matter halo. So importantly, you don't just have a halo and the galaxy inside, but actually galaxies like the Milky Way have satellite galaxies. So the Milky Way has at least 60 satellites. And we think each of those satellites, those dwarf galaxies, is in its own subhalo. So what you're seeing here is not just a halo, but also these subhalos. And these subhalos are going to be home to other galaxies that are in orbit around this primary galaxy. So the question of the galaxy halo connection is, for example, if I give you the mass of this halo, how many subhalos do I expect to form inside of it? What is the mass of the primary luminous galaxy that's going to form inside of it? And what are those dynamics going to be? And how is that going to evolve in time? So as an example of the kinds of questions that we're asking right now and that we don't know the answer to, I think that this is an exact case in point, this galaxy halo connection, trying to figure out what we call the subhalo mass function, but the distribution of what the masses of the subhalos are going to be, for example. So this is a big problem. I'm active in research in this area from the point of view of a particular dark matter particle that I'm very focused on. And so I just want to give you all kind of another way of thinking through that picture that I've just been showing you. So here is a slightly more realistic, less cartoonish figure of our local galactic group. So you see the Milky Way here. You see Andromeda, which is our largest near neighbor. So Andromeda and the Milky Way are actually on a collision course. And it's interesting to tell people this because I think like we all imagine collisions as like things really like my fists hitting each other, right? You can hear my rings hitting each other. The collision course here is actually going to be a lot less violent, right? Because the distance scales involved are so large that really we're just going to be thinking about things becoming gravitationally entangled with each other rather than actual like violent explosions and that kind of thing. But what you can see on here is that the Milky Way has satellite galaxies. So this is just some of them. You can see here, I know the text is a little bit small and I wish this was a higher quality figure, but you can see the Large Magellanic Cloud. So you may have gone out and looked at that with a telescope, or the Small Magellanic Cloud. We have also some galaxies that are named after their locations in various constellations. So the Ursa Major, 1 and 3, and the Ursa Minor, Dwarf, etc. And similarly, Andromeda has its own satellite galaxies. And there are these dark matter halos that are surrounding the galaxies. And then there is also dark matter that's linking them. And that's in part how we're in the same local galactic group. So this is a very exciting thing to try and understand. And actually what's really neat, particularly about our local environment, so just around the Milky Way, is that we are just starting to get incredible sets of data, for example, from the Gaia instrument about the Large Magellanic Cloud, where we're actually starting to understand how stars are being tidally stripped off of the Large Magellanic Cloud by the orbit with the Milky Way. So the Large Magellanic Cloud is a relatively recent in cosmological timelines capture by the Milky Way into its gravitational well. And so we are, in some sense, able to see in real time what are the gravitational dynamics here. So again, just to give you a picture of what this looks like from the point of view, if you're trying to imagine what does this look like from the ground. So here's a really beautiful piece of astrophotography by Anja van der Linden. And here is a figure that Ethan Nadler gave me permission. So Dr. Ethan Nadler, who is a postdoctoral researcher at Carnegie Observatories and the University of Southern California, overlaid where we expect these dark matter halos to be. So the next time you have the opportunity to see a dark night sky, I want you to look up and think about how much we are not seeing in the universe. So I told you very little about the properties of dark matter, and the gist of it is that actually we don't know very much about dark matter. So over the years, theorists have come up with a lot of different ideas of what dark matter possibly could be. So what you're looking at is the Venn diagram to end all Venn diagrams. This is one that was developed by Tim Tate. He's the chair of the physics and astronomy department at UC Irvine. This is also an updated version of the figure that various physicists have shared Tim's work over the years. I had him update it to include primordial black holes before I included this figure in my book. So again, I encourage people to pick up the book or any of Tim's work to learn more about this. I spend most of my time, and unfortunately I won't have time to talk about it, living in this axion-like particle corner. But one of the things that's like generally really exciting about dark matter as a problem from the point of view of theoretical physicists is that it is a place where we can spend a lot of time in the sandbox, playing around, coming up with ideas and running simulations to see how they unfold. I also just want to mention that there are different ways that we can probe dark matter. So we can do direct detection, where dark matter interacts with standard model matter. So the standard model of particle physics is all of the particles we have ever actually seen. We can also look for direct detection, where dark matter produces standard model matter. And some of this is also happening in particle colliders, where you collide standard model particles together to see if they produce dark matter. Right now, I'm helping to lead the cosmic probes of dark matter effort as part of the US SNOMAS process, which happens about every 10 years and determines what funding will look like. So I'm particularly interested in how we will use astrophysical probes. So as an example of something that's going to produce a lot of data over the next decade and where a lot of simulation work is happening, you might recall that I mentioned that Vera Rubin was one of the people, and she's really the astronomer who's credited with first making the case for dark matter as a real, not hypothetical problem, but problem based on observational data. We now have the Vera Rubin Observatory that's under construction in the Atacama Desert in Chile. And this is an instrument that is going to come online in about a year and a half and start producing first light, first data. This is going to give us so much insight into the subhalos and structure formation and allow us to compare our simulations against our theories and our observational data. So I'm a proud member of the Vera C. Rubin Observatory Dark Matter Working Group. And in fact, as part of it, I have been the one leading responsibility for making the case for wave dark matter searches with Vera Rubin Observatory. I also just want to mention that high energy astrophysics, so X-ray, gamma ray observations, are potentially the future of high energy physics and dark matter searches. So we're going to find out this week, maybe on Thursday, whether Strobeck's a proposed X-ray space telescope with NASA, where I'm leading dark matter searches, will actually be funded. So there's a lot of different ways that we are doing searches for dark matter. And I just want to mention a few next steps that are relevant to this audience, in particular, people who are thinking about large amounts of data. So we're now in my research group starting to use machine learning techniques to look for gravitational lensing. And the goal of this is to look at how dark matter distorts space-time so much that it looks like a funhouse mirror and you get replicated images. So this is what gravitational lensing is. We're hoping to predict what these signals will look like for next generation experiments like the Vera Rubin Observatory if the dark matter is the axion. So I want to encourage people to invite the postdoctoral researcher who's working in my group, Dr. Nathan Musoki, that's him on the right, to come talk to them about this. He's an incredible computational cosmologist. And I are working with Dr. Brian Nord, who is a scientist at Fermilab in the University of Chicago. Brian is probably, I don't know if he's the world's leading expert on artificial intelligence in cosmology, but he's definitely up there. So these are people that folks should be talking to. I also want to point out the three of us, we're all African descended cosmologists. And so when we're talking about the future of dark matter, this is what the future of dark matter looks like. And I just want to end by pointing out that science is shaped by the stories we tell about who matters and whose ideas count. And so I want to point out that an experiment that a group of us ran was this Rainbow of Dark Sectors virtual conference at the Aspen Center for Physics. I was part of the team that proposed this. So we ran this conference basically to bring people together to talk about dark matter. But what we did differently is that we integrated talks about equity and justice into the science sessions, with the understanding that addressing equity and justice issues within the physics community is part of how we are going to address the dark matter problem, because making sure that it is a safe and welcoming space for everybody is part of how we tackle scientific problems. I just want to point out to people that one of the reasons we thought about it as equity and justice and not diversity and inclusion is because thinking through diversity and inclusion as a framework actually doesn't do anything for folks like Breonna Taylor. And so that is part of where the space that I'm thinking from is, what do we do to change the material conditions under which, for example, Black lives, Indigenous lives are lived? If we are only thinking inside of our bubble of what do we do for Black people who have survived to be in the classroom, who have survived to parent children who will end up in our scientific classrooms, we have not thought broadly enough. And so when people are thinking about justice, I don't want it to just be about ending racism in the classroom, but it has to be ending racism in our communities, because before a Black scientist gets to their lab or their classroom, they walk out their front door. Finally, I just want to say that we need to think broadly about making sure that children all have access to a dark night sky. And I want people to understand that thinking about true access to a dark night sky and having the experience of wandering under it the way that our ancestors have for generations, this is part of how we have evolved as a species. requires radically rethinking how resources are distributed in our communities and making sure that people are not hungry, that people are housed, that people have clean water, that Indigenous sovereignty is respected, that we have clear skies that are not being polluted by a poorly regulated, pardon me, poorly regulated artificial satellite constellations. We need true accessibility, and we need to think about how prisons and the system of mass incarceration is damaging. When we end colonialism, I think we will be in a better position to confront the challenge of global warming. And so I want people to think about freedom dreams under a night sky. And we're really just beginning in a lot of the work that we do. I just wanted to end this slide by giving credit to the incredible team that works with me. So these are my graduate students, my undergrad and my postdocs. We're doing really exciting things. We're just beginning. We are at the end of the talk, and we have, I think, a few minutes for questions. I want people to understand that cosmological storytelling, which is what I do, I'm a storyteller, like liberation struggle, is a fundamentally human activity, and it produces a lot of data. So like this woman in Haiti who is struggling for liberation for her people, as Haiti has been doing for centuries now, we should think about how doing cosmology sanctifies our humanity, and how sanctifying the humanity of people who are struggling for liberation should be part of our cosmological storytelling. Thank you.
Chanda, thank you very, very much. My mind is a bit blown at the moment. I must say, I'm just trying to get my head around dark matter not actually being dark, but being a mass that we don't necessarily see. And lots of people, I think, have been responding as well with questions. So we've got about 7 minutes. So are you up for some quick fire questions, perhaps?
Yes, let's do it.
Brilliant. Okay. Here we go. So Rocio de la Cruz says, thank you for this impressive session. How do you envisage open data and data sharing between researchers helping with the progress on theories? And would that include sharing satellite collected data?
Yeah, so this is an interesting question, and I've just backed up. Can people still see my slides? Sorry.
In the Vera Rubin Observatory.
Yes, okay, excellent. So I wanted to back up to this because one of the conversations that we are having in the astronomy community is about how data and resources are distributed. So for example, building a facility like this is incredibly expensive and requires partnership and careful management of relationships, for example, between people in Chile, people in the United States. This is primarily an American project. The data sharing agreement for this particular experiment is that anyone based at a US institution has the right to join the Legacy Survey of Space-Time, which is what this instrument used to be called, was LSST. Other countries that want access to this facility will have to make in-kind contributions, and those are carefully negotiated contracts. This is one model that's like semi-open in that anyone in the US can join, and there are pathways for people outside of the US to join. So I was actually just meeting with Mexican researchers last week who are making in-kind contributions in order to access this data. But there are other models, and there are worse models. So the one time that I have actually been observing, because some astronomers thought I should understand how data is actually collected, I went to a facility that is privately owned, also in the Chilean desert, actually not very far from where Vera Rubin is being built. And that's a telescope that will never be usable to the broad community. There's no way to apply for time, and then unless you're at certain institutions. So I was able to go because I was a postdoctoral researcher at MIT. So I think these questions about data are not just about what happens to the data once it's already been captured, but also who gets to participate in making the decision about how the facility will be used.
James Guff says, great talk, Chanda. And he picked up on a figure I picked up, actually, that in a galaxy, I think it's 20% is luminous, but 80% is dark matter or subluminous, invisible matter. And James is asking, well, what data? How did you get to that conclusion? How did you get to those figures?
Yeah, so let me see if I can, good. So this particular, I want to point people to this figure again. So this is actually almost a first year undergraduate physics problem. So if anybody's taken undergraduate physics, you can root around in your brain looking for that information, or for those of you in the UK, this would definitely be A-level material. There are two ways to kind of measure how much matter there is in a galaxy. So you can look at how fast stuff is moving in the center, around it, the center of a galaxy. And there's actually like a first year A-level undergraduate physics equation that gives you the relationship between the velocity, the distance, and the mass. You can also look at how bright the galaxy is, and the amount of light that's being radiated is going to tell you how massive the galaxy is. So another way of thinking about this missing matter problem, this invisible matter problem, is that there is a mismatch between those two measurements. When you look just at the luminous matter, it tells you this is how massive the galaxy should be. But then when you look at how the stars are moving, the calculation for the mass gives you a completely different number. So that was the first way that we actually figured that out. I had to force myself to take a bunch of slides out of this talk that talked about other techniques, particularly gravitational lensing. You can actually calculate how much dark matter is causing these distortions in space-time that literally look like a funhouse mirror. I wish I had put it in as a backup slide so I could show you, but Google gravitational lensing and Hubble and you will find it.
To bring this, obviously all in line with what we're doing today, is there anything the open data community can learn from the work around equity and justice in the dark matter community?
Yeah, I really want to point people to this model that we used with the Rainbow of Dark Sectors conference. So this conference was put together by a subset of people from I guess the collective, as we might call ourselves, of Particles for Justice. So I encourage people to go to the Particles for Justice website and have a look at the work that we are doing. But I thought this was a really innovative approach that actually would have worked even better. It was planned for an in-person conference. And then, as everybody knows, we've been living through this pandemic. For the in-person conference, what this means is that when you have a talk on dark matter, in a single session, and then you have a talk about equity and justice squeezed in between the scientific talks, people actually feel a little bit of social pressure to not get up and walk away during the talk on equity and justice. So at the very least, you're doing a little bit of education for people, and people are learning things along the way. And you're also setting the standard that it is normal for people to mix these things together and be concerned about them as scientific problems. I also want to add that we didn't just have these talks, but we actually brought people together to start thinking about how they were going to make contributions to the snowmass process that I mentioned earlier, to talk about equity and justice, to actually advance these issues in a practical way. So it can't just be listening to talks, right? Then people have to go off and do something. And we tried to pull those two things together as part of also don't just listen to talks about dark matter, but go off and do theory about it, go off and collect data about it.